Hey guys, this is Professor Janacek, and I would like to talk to you about the fundamental theorem of calculus. This is fantastic. You are going to love this. Let's begin. We'll let f, that's lowercase f, be a continuous function on the interval from a to b, and we'll let uppercase f be any antiderivative of lowercase f on that same interval. Then we have the integral from a to b of f of x dx, so that's the definite integral, is equal to, now we start by writing this interesting little notation where we take uppercase f, remember uppercase f is the antiderivative, so that's how we're first going to evaluate these. Find the antiderivative first. And then we have this bar next to it, this vertical bar followed by the limits of integration. The lower limit of integration is at the bottom and the upper limit of integration is at the top. That tells us we are going to evaluate it, and the notation for that evaluation, the way we actually do this notation is, work this notation is here on the right. That tells us that we're going to take uppercase f of b minus uppercase f of a. So let's take a look at some examples and you'll see how really great this is. So let's start with example 1 here. We're going to integrate from 0 to 10 of 60x minus 6x squared dx. So to begin with, we'll start by finding the antiderivative of my integrand. The integrand here is 60x minus x squared. The antiderivative of that is, we take 60x, take that exponent, add 1, and then divide by that amount. Do the same thing with the 6x squared, take that exponent, add 1, and then divide by that amount. And then this can be any antiderivative, so I'm going to take the antiderivative that rather than writing plus c back here, I'm going to make that plus 0. I can choose 0 as my constant because I'm looking at any of those antiderivatives. And then we use the notation, we're going to evaluate that from 0 to 10. So what this gives us, I can simplify this just a bit. This is 60 over 2, which is 30 x squared, minus 6 over 3, which is 2x cubed, again evaluated from 0 to 10. So that notation tells us we will take 30, and give myself a little more room, 30 times x squared minus 2x cubed, evaluate that at 10, minus, then we're going to take that whole expression and evaluate it now at 0. Be careful with those positives and negatives. If we simplify this out, let's see, what is that? 10 times 100 minus 2 times 1,000. That looks like it's going to end up being 1,000. Of course, the second one ends up being 0, so we just subtract off 0. Pretty simple. Not too bad though, right? The hardest part for this really can end up being just this computation. So take your time with those computations. Let's take a look now at example 2 here. We're going to integrate from 0 to 2 pi of 3 sine x dx. So to start with, we will simply take a look at our integrand here, 3 sine x. We want the antiderivative, any antiderivative. Well, let's see, the antiderivative of sine of x is negative cosine of x, so that means we get negative 3 cosine of x. Again, instead of that arbitrary constant that we often add there at the end of the indefinite integrals, I'm going to choose the constant of 0 since I can select any of those. Now we're going to evaluate that from 0 to 2 pi. So this gives us negative 3 cosine of 2 pi minus negative 3 cosine of 0. Well, cosine of 2 pi is 1. Notice we have minus a negative. I'm going to change that to a plus there in the middle. Cosine of 0 is also 1. So we end up with negative 3 plus 3. Oh, look at there. This one just gives us 0. All right, now let's take a look at example 3. We're going to integrate from 1/16 to 1/4 of the square root of t minus 1 divided by t dt. Notice the variable has changed here to t's and not x's, but it works similarly. I think the first thing to do is to simplify that integrand where it's something I can find the antiderivative of easily. So I'm going to keep my integral notation there in the front. I'm going to write this as t to the 1/2 power divided by t minus 1 over t dt. So all I've done is rewritten that integrand. We can simplify this. T to the 1/2 over t, that's t to the negative 1/2. Now I'm going to go ahead and leave this 1 over t in the integrand for a reason, because I recognize what the antiderivative of 1 over t is. Don't know about t to the negative 1, but in the 1 over t form, I might recognize it a little easier. I'm not going to use the power rule on that, or the antiderivative of the power rule on that second bit. So let's go ahead now. I think we're ready to find the antiderivative here. So we'll take t to the negative 1/2, we'll add 1, and then divide by that exponent, minus, again, I'm not going to use kind of the antiderivative power rule. The antiderivative of 1 over t. What do you take the derivative of that gives you 1 over t? Well, that's the natural log of the absolute value of t. However, I notice that my t values are both positive, right? I'm going from 1/16 to 1/4. Those all stay positive, so I don't need the absolute values on there. Again, I don't need the plus c because I can choose any antiderivative, so I'm choosing the constant of 0, but I do need to evaluate this from 1/16 to 1/4. Let's go ahead and clean this up just a bit. This is t to the 3/2 power divided by, 3 to the, that's a negative, watch those, let me clean that up. This is a negative 1/2 plus 1, that's no better. Negative 1/2 plus 1, so it's t to the 1/2 power divided by 1/2, that's going to be 2t to the 1/2 power minus the natural log of t, evaluated again from 1/16 up to 1/4. Let's go ahead and evaluate that now. Notice we always evaluate at the upper limit first. Minus, and then we evaluate at the lower limit. All right, let's clean this up just a little bit. Raising something to the 1/2 power is the same as taking its square root. The square root of 1/4 is 1/2. That's going to work out to in our favor. Also, I'm going to recall some properties of natural logarithms. So to prepare this, I'm going to write this as, instead of 1/4, I'm going to take that, write that as a 4 to the negative 1 power. So it's the natural log of 4 to the negative 1. Do some similar stuff here in the second, for the second bit. The 1/16 to the 1/2 power is the square root of 1/16. That gives us 1/4. Minus the natural log of, instead of 1/16, I'll write that as 16 to the negative 1. You'll see why I'm going to do that here in the next step. 2 times 1/2 is just 1. And then properties of logarithm says if I have an exponent on that argument, I can multiply that to the front as a coefficient. So I actually get plus the natural log of 4 minus 2 times 1/4 is 1/2 minus natural log of 16 to the negative 1. Again, do that little trick with logarithms. Love the properties of logarithms. I now have plus the natural log of 16 there in the back. If we distribute that negative there in the back, we have minus 1/2 minus the natural log of 16. Putting these things together, 1 minus 1/2 plus the natural log. I don't need to write parentheses on that. You can see this. 1 minus 1/2, we'll put that together. The natural log of 4 minus the natural log of 16. We can actually put those together as well. 1 minus 1/2 is just 1/2. The natural log of 4 minus the natural log of 16. Those are both natural logs. They have the same base, so I can put them together. 1 natural log. And then we actually take the quotient of those arguments. So it's 4 over 16. Again, gotta love the properties of logarithms. So that gives us 1/2 plus the natural log of 1/4. Yes, you could write that as 4 to the negative 1. Which could also be written as 1/2 minus the natural log of 4. And there you go. Enjoy.